saving. You probably know also from Jim Kim that when Brazil made it a decision to break the patents on HIV drugs and make their own HIV drugs, and spent the money to make those drugs and distributed them to people in Brazil who were HIV infected, they actually came back and found out that after a few years they were saving money by treating people with HIV. We know that we can save lives, and if you want to look at it in the most kind of cost-effective sense, we can save money by treating people with HIV. But the problem is that the need for treatment outstrips available funds. So the need grows every year. You can see on this graph here that the bar is going up. How much it will actually cost to treat people living with HIV infection is going up, whereas funding has remained relatively flat. And when you put this actually in the context of other things that we spend money on, we ask, is this idea, this concept that everyone in the world should have access to treatment for HIV, asking too much? Are we caring about something that is simply not achievable on a dollars basis? Well, it has been projected by Jeff Sachs, a noted economist, how much it would actually cost to treat everyone in the world if we were to make that decision. And the total is $4.4 billion per year. Is that a lot of money? Well, $1 billion sounds like a lot of money, but in actuality, we've spent already $500 billion in Iraq alone, not counting Afghanistan, just talking about Iraq. So when you put the numbers in context, you see that this is actually achievable. It would cost $20 per person in the United States per year to treat everyone with HIV infection. And to me, that seems like a totally achievable number for which we have no leadership, and it is really leadership that we need. The problem is that we don't have those medications. They're not getting out to the people who need them. And this young child who lives in Sikoro, which is where we are working in Western Africa, has really no clinic to go to. She has no doctor to go to. She has no medicine that's accessible to her. She, in fact, if she were to become sexually active, doesn't have access to condoms, because in West Africa, to purchase a condom costs as much as a meal, and most people choose to eat. So her hope of preventing herself from getting HIV infected in the future becomes slim to none. So a vaccine is really the best hope for HIV infection. It is something that you could give to people and prevent, theoretically, HIV for the rest of their lives. It could save millions of lives, even a vaccine that's not completely effective. For example, what's shown here is if you had a 30% effective vaccine, you could actually save 5.5 million lives. A 70% effective vaccine would save 25 million lives. Oh, my glasses, 28 million lives. So you can see, even with a vaccine that's not 100% effective, we might actually be able to save that little girl's life in Sikoro, Mali. Now, why does it take so long to make an HIV vaccine? We've known about HIV for years, since 1983, as a matter of fact. Why does it take so long? In truth, as many of you sitting in this audience who are biologists know, it does take a long time, first to discover the pathogen, then to figure out what are the correlates of immunity, what are the critical antigens, how to make the vaccine, how to formulate it, how to test it, and we'll talk about that a little bit. 25 years is average, but we are at that point right now. And what you've heard in the news, perhaps, is that the latest big vaccine trial, the Merck vaccine trial, failed. And so people are beginning to despair. Will we ever have an HIV vaccine? So let me just go over a few of the aspects of HIV. I promise you not too much immunology for those of you who are not aficionados, and just enough for those of you who are. But I want to talk about why it's so difficult to come to the point of making an HIV vaccine. One of the reasons is that HIV is a retrovirus. It is a virus that makes RNA as its message. And typically, most viruses that use that mechanism of transmitting their message to their next generation, RNA is prone to making mistakes. The process of replicating RNA is prone to making mistakes. Another virus that is an RNA virus is hepatitis C. We don't have a vaccine for hepatitis C either. So when HIV gets into the cell, it basically uncoats, it takes its RNA message out, it converts that into DNA. The DNA actually can integrate into the host genome. So people living with HIV have the HIV genes integrated into some of their cells where it can stay quiescent for a very long time. And then once the cell becomes activated, then the genes start getting transcribed and translated, making protein, making the virus, and then bursting out of the cell. The biggest problem in HIV vaccine development is this. When it enters the cell, normally you can make an antibody to protect against entry. That's how we protect against many viral infections. We make an antibody that blocks the entry. The HIV virus has a special trap door. When it approaches a cell, it opens that trap door, and then a protein comes out and allows it to enter. That happens in a microsecond. The space involved between the HIV virus and the target cell is so small that an antibody can't even actually fit into that space. So no antibodies have ever been identified that really effectively protect against HIV entry into the cell. They are looking at single-chain antibodies that might fit in there, but basically one of the biggest problems is how to protect using antibodies, and it's not ever been shown to be effective with the exception of just a few, which we can talk about later. This is what CD4 T cell looks like as the target of the HIV virus. The CD4 T cell is the factory for HIV infection. In fact, it makes all of the T cells in the body make 100 billion new viral particles every day. Now remember the other point about this, each one of those particles might not actually be the same as the one that came before because this is an RNA virus and it mutates. The other point about this virus is that it attacks the T cells, so that factory is destroyed in the process of creating new HIV particles. The T cells decline, and then the person has immune paralysis. Without T cells, you can't fight off infection. That's why we have AIDS. Now, to go back to the concept of the HIV virus mutating, this, you probably are very familiar with the concept of evolution. And in every HIV-infected person's body, HIV evolution is going on. What happens in the person's body is the virus is mutating, it's trying out new forms. If an immune response occurs to the virus, then it will mutate away from that immune response and become immune to the body's attempt to fight it down. So the host cell is infected, the virus is being produced, the virus is mutating, the immune response is occurring, and yet it is ineffective. There are two processes between HIV evolution, and one is drift, and the other one is selection for more fit virus variants. When we first started talking about this in 1996, people were unsure that this actually went on, but in point of fact now we know that due to the mutation of the HIV virus, that it is able to create versions of itself that completely escape the immune response. How does that happen? This is a picture, for those of you who like graphics, of a virus entering a cell, the target cell, which is the CD4 T cell, and then it's making more copies of itself. That cell is actually when it's able to present immune information to the immune system, is breaking up the virus and presenting at the surface of the cell a very small piece of the virus called a peptide or a peptide epitope.